Swayam Prabha. Digital India. Educated India.
In the last class, we discussed about vibration transducers, and with the understanding of in particular the piezoelectric accelerometers. In this class, we will see how in different practical scenarios vibration measurements are done actually using piezoelectric accelerometers, and how do you actually monitor the vibrations of a machine, be it over the time or be it just for diagnostic measurements and so on. Okay. So, typically when you will come across many industries, be it cement plant, steel plant, power plant, etc. Basically, you will be coming across many rotating equipment wherein whose vibration has to be monitored, measured and recorded and so on. And you see here this is a torsion shaft which is rotating, which is supported on the bearing housings, and then you will see this couple of few cables coming out here. These are actually accelerometers which you cannot see here, and then they are installed just to record the vibrations level, and then we can bring back this recordings to the lab and do the analysis from a diagnostic point of view. But another very important aspect of vibration monitoring is, like I had mentioned to you in the last class regarding a standard wherein the vibration monitoring has to be done, so that the vibration levels are not above a certain permissible limit. Similarly, because we are talking about vibration monitoring, I think it is important that you should also know that there are limits of vibration level for human vibration level limits. There are standards to that. In particular, wherever we have human operators holding on to devices which are vibrating because of their functionality. For example, one is the steering wheel of a vehicle. Okay. One may be the jackhammering handle. If you go to any construction site, you will see people will be using the jackhammer drill to break in concrete, etc., and they produce a lot of vibrations on the handle. Okay. These are certain scenarios wherein harmful the vibration levels could be harmful, and we have to be ensuring that the vibration levels are not beyond a certain level. And of course, one is the machine level. Of course, I will not put it here. Another is the machine level, machines. So, we had had some clue as to that standard, which says depending on the power of the machine, what is the permissible limits of the vibration level. Similarly, for human vibration levels, there are ISO standards as to what the permissible level should be, and I thought I should mention this in this class. That is the ISO 2631 standard. If you look here, and this is the permissible limit, ISO 2631 human vibration limits, subject to different frequency bands in octave, in 1/3 octave till about 1000 hertz. This is in the x axis. This is the RMS values of the velocity in this curve, and the RMS values of the acceleration in this line here. And for 4 to 8 hours of continuous holding on to a device, what should be the permissible level is given by this line here, for 2 to 4 hours, for less than half an hour. So, these are the limits as per ISO 2631 standard. So, if I have any operator holding on to a steering wheel for 4 to 8 hours, the maximum RMS level should be in this band, below this level. So, these levels are there. We are not, of course, in machinery health monitoring, we are not talking about how to ensure that the levels are less, but I thought you should know in this class that there are also standards for human vibration levels. For example, another is the car seat vibrations. The human seat, your body is sitting on a platform. What should be the maximum allowable level of the vibration to the seat, and that is also there. Okay. These are for holding hands, for human body positions. There are different levels also. You can see that in the standard. Just as an example, I will maybe go back to this slide first. This is a tractor, okay, wherein this steering wheel was having excessive vibrations. Okay. And this relates to a little bit of diagnostic procedures as well. So, what happens, this level of the steering wheel was much higher than the permissible levels, and as soon as the engine was starting to idle, okay, the vibration levels were high. You must have noticed it in many of the particularly in diesel engines, not in the modern cars, of course. If you think of the old Jeeps, etc., you will see as soon as the engine is starting, your steering column would rattle, and then there will be heavy vibration levels. As per international standards, are they acceptable? We do not know. Okay. Are our products marketable? No, not because of the international standards. So, in this particular case, what has happened is the firing frequency which is generated by the engine firing frequency was almost close to the steering wheel resonance. Okay. So, no matter how good a steering wheel you design from a strength point of view, from a damping point of view, not from a damping, from a mass or a stiffness point of view, you will not be able to stop the motion of the steering wheel, because it is vibrating at its natural frequencies, which is what is the forcing frequency? It is the engine firing frequencies. I cannot change the engine firing frequencies, because that is how my engine is designed to operate at a certain RPM. It has so many cylinders, it is a 4-stroke engine, and so on. So, and its idling RPM is fixed. Okay. So, if the engine firing frequency cannot be changed, all I can do is change the steering wheel's resonant frequency, and that is how it was done using the finite element methods. We can design the attachment locations. Okay, we can change it. You can see this is a 3-spoke steering wheel as opposed to a 2-spoke steering wheel. So, just by changing the design of the steering wheel, we will change the natural frequency and shift the natural frequency away from the forcing frequency. So, to avoid resonance, condition, through design we can change that, okay, and then we can shift the natural frequency. Now, if your engine idles, the steering wheel is not going to vibrate. Okay. So, now how do we do the vibration monitoring here? Of course, you do not see this accelerometers. If you see the clips, there are locations. Even sometimes you can mount accelerometers on clips. For example, this is the plastic cover on the steering wheel skeleton. Okay, as a molded plastic, wherein we can put a clip on this clip. You can mount the accelerometer. Okay. Now, how do we do the rotational speed monitoring? Okay, and sometimes we can use the reluctance type pickup. Sometimes we can use also a photo tachometer, wherein of course this is a shiny surface. So, if you shoot a light beam, okay, and if there is a shiny patch, it is going to reflect back. Okay. Or if you can in fact, there are shiny patches you can fix here. And then you can have a frequency counter. And then we can measure the rotational speed, or you can record it as well. Okay. And this is out of a gearbox. Okay. And if you will see here, we have you can see a shiny white aluminum block. Actually, it's an aluminum block, wherein this is the casing of the gearbox. It is not possible to tap it. Okay. At this site. So, all we did was put a mounting block and glued it with a cement. Okay. And if you will see couple of holes here, one hole here and on the stud coming out on this accelerometer block, we can either screw on the accelerometer to measure the acceleration. I will show you another view. And this is how dirty or unhealthy or conditions are there in the actual industry with gears everywhere, grease everywhere, etc. I obviously cannot put, and there is no space to, and they are always rotating, plant would not shut down. So, what we have done is glued these blocks, mounting blocks. We just clean the surface, clean it, remove it of grease, put a cement, and then it sticks. Almost instant glue is there, and then you can put this block onto this block. You can screw the accelerometer, and this is the rotary kiln I was talking about in a cement plant actually. Okay, and this is the plumber block which is used to house the bull gear. Okay. And this is another view wherein we can see the accelerometers. This is a triaxial accelerometer. You will see these 3 cables coming out, okay, wherein we have put this block. Okay, and then we can orient this direction to see the measure the vibrations in the 3 directions. Okay. So, as I was telling you, vibrations in 3 directions is always very important from a diagnostics point of view, whether we want to measure the radial vibrations or the axial vibrations at that particular location. And typically in any plant, you will see the configurations of the machineries are a prime mover being driven by a machine being driven by a prime mover. This prime mover could be a electrical motor or an IC engine, and this is the new ISO 10816 standard, which says the allowable vibration level for a particular machine, and the ISO 2631 was for the human being and ISO 10816 is for the machines, which says we have to measure the RMS vibration level in the frequency range from 10 hertz to 1000 hertz. Vibration level has to be in the velocity mode, that is either in meters per second or millimeters per second, and then there are 3 levels of vibration, whether the machine is acceptable, machine is an intermediate stage, or the machine's vibration are unacceptable. The machine has to be diagnosed and corrected, and of course, these levels depend on the machine power. And just for example, if it is a 1000 kilowatt machine, this vibration in the highest vibration in any direction has to be 3 millimeters per second. Okay. and this standard only tells you about the overall vibration level, and then we have to ensure whether it is acceptable, not acceptable. So, if you just have a vibration meter and an industrial accelerometer and you go around different places in your plant and just measure the vibration level itself and come up with the values, that itself is a good survey to ensure that whether the machines are okay or not okay. Okay, if you just follow the standard, and many industries definitely do that. But the problem which we have as a machinery fault diagnostics engineer is, what is the real cause of this levels of vibration if they have exceeded, and for that we need to record the vibration level, do a spectral analysis, find out these frequencies at which the levels are high, and then try to relate why these frequencies are high, which is the physical parameter which has been responsible for making this level high, and then how do we correct it. Okay. And typically, if you go to any plant, this is how the configuration is. So, this is the prime mover, this is the mechanical unit, and this is usually a coupling. Okay. This prime mover could be a electric motor. This could be a gearbox, could be a pump, could be a blower, could be a fan, usually. Okay. And they have to be put on a foundation. Okay. And this could be driving some other things, and this is typically the configuration of the machines in 90% of the cases. Okay. And we have to capture the dynamics of this system, that is our objective. So, what are the good places to capture the vibrations? Of course, we have a bearing here, this is the non-drive and bearing NDE. Similarly, we have the DE, and this we have another DE, another non-drive end. Okay, and coupling. I will mark the ideal locations of the accelerometers. Accelerometers should be kept close to this location, close to this location, close to this location, close to this location, sometimes close to the foundations. These are the typical positions of accelerometers. We should definitely avoid places like just put it on, because this casing is very important, just to put it here. It is accessible, easily accessible, you just put one accelerometer here. These are not the good places. Okay. Not desirable. Okay. I will enlarge one of these views here and try to explain Suppose I have a shaft and then I have a bearing. The shaft is rotating and then shaft is put on a casing. Just one view I am drawing maybe. This is some machine component and this is our shaft. See, these are not good locations to keep your bearings, to put the accelerometers, because they are far away from the dynamics of the system. Okay. The best location would be, maybe this is a good location, this is another good location. Okay, we are as close to the bearing as possible. Okay, sometimes this may be too thin, so we should try to go for a thicker system wherein the dynamics is captured. Okay, in a system there is no, if this extended like this, no, these are not good locations to put accelerometers. So, we have to be accelerometer has to be mounted close to the generation of the vibration, because this shaft, if it was misaligned etc., the forces would come at the supports, at the bearings, and this is where a lot of motion will be there. If I measure here, they will have very poor signal to noise ratio. I may get something, but they will be buried with a lot of noise. Okay. So, you have to be very close to the generation of vibration, and that is why when you need to do an initial survey of a machine for doing vibration monitoring, you have to ensure, try to find out where the bearings are located, where the rotors are located in a motor, okay, where are the loose foundations, okay, where are the impact forces being generated, etc. So, these are the places which we put the vibrations, not on a flashy control panel, a lot of meters there, you just put an accelerometer there, no, definitely not. Okay. These are places where we should not put the accelerometers. Okay. So, this is with this in mind, I will show you another case wherein we have actually a typical case motor gearbox. This is the top view, okay, and there are so many different locations wherein the vibrations were monitored. If you see the black ones, they are the bearing locations. This is 13 is the non-drive end bearing, 16 is the drive end bearing, and this is a 3-stage gearbox. Okay, so there are shafts like this: intermediate shaft, input shaft, output shaft. So, these shafts are supported on bearings 2 and 7, 3 and 8, 4 and 9, and then this is a bevel gear. Okay, so there is a power shaft here. So, there is another bearing here, and on top of it, every foundations of this motor, 4 foundation gearbox, 4 foundations, they are measured. And just for comparison, another point outside the system is measured, just to ensure how high or how low the level outside are. And in foundations, depending on the configuration, foundations could be of different types, okay, whether it is on the concrete, whether there is a steel frame, another structure, etc. And and then of course, the direction is axial, horizontal and vertical is coming out of the plane of this projection here. So, you see in all this for vibration monitoring, if there are 18 locations and every locations I am having 3. So, 18 into 3 channels of 54 channels of vibrations are recorded. So, if I was to measure simultaneously, I need to have a system which will take in all these recordings together. But and because that will help you do from a diagnosis point of view. If they are measured simultaneously, I will return the phase information, relative phase between these signals, okay, and then that will help me. But sometimes just even a single channel FFT also gives me some clue as to what the vibration levels are. And this is the typical arrangement wherein you will see this is the coupling here and this is the gearbox, okay. And actually this gearbox was used to convey raw materials on a conveyor system. If you will see here, this is the motor here and this is the gearbox, okay, in the motor. So, you will see a bevel gear arrangement wherein there is a 90-degree reduction in the power transmission direction, and this is driving a conveyor system. And you will see these are the bearings, if you are marked here 1, 2 etc., they are different bearings for the intermediate shaft, and they are put on a concrete platform onto which there is a steel frame, on which these steel frames are normally there to ensure that the alignments are perfect between the gearbox and the motor, so that the horizontal, this shaft remains horizontal, perfectly horizontal. Sometimes once we have the steel structure, it is very easy to put in shims, so that the alignment can be done, and that is why, and they can be all manufactured in one piece and the foundation is put. So, that at site in fact, at this location, this was about 100 meters from the ground on a platform made out of concrete, and because the conveyors were coming out from large ships and they are high over the ground, and obviously there because this floor, if it is not on level, this system could be having a misalignment. So, lot goes on to ensuring that the shaft between the motor and the gearbox are on level in the same horizontal plane. Even a variation of few millimeters or microns is going to affect the dynamic forces. So, perfect alignment has to be done. Imagine 100 feet or 100 meters above the ground, you are doing such an arrangement, and then how do you ensure that they are all aligned, and these are provisions wherein shims can be done. And to ensure that the vibration levels are less than the levels allowed as per the ISO standard, we have to monitor at all these possible locations, in 18 locations in this case, 18 into 3, 54 locations, and see what is the highest levels and whether they qualify the standard of the vibration. In fact, in this case we had situations where the manufacturing was so poor that the alignments were not done. There were a few welders, I do not have a better view here, but they were lying because this was used to unload raw materials from the ship. So, obviously, you can imagine that this is near a seashore, and seashore the environment is very salty, corrosive air is blowing, and this system which was lying there for about 2-3 months on the monsoon and on a corrosive wind, you can see a lot of corrosions occurring in the foundations here, corrosions on the motor base as well, and this will weaken the structure. On top of it, if you want to not do a perfect alignment, a lot of sources of high vibrations can arise. No matter you may be having a very good new gearbox, new motor, new bearings, but your misalignment in the foundation, this is going to give you a lot of high levels of vibrations. And in fact, this is where the ships come in unload coal. As you know, our country, we do not have good quality of coking coal, but we have good quality of iron. So, we export iron ores. Okay, the same conveyor systems. One system is used to export iron ores onto the ship. Another conveyor takes in the coal from the ship, and this conveyors go to large silos wherein we dump the raw material, and then there are stakers and reclaimers who will take this coal which we import and then put it on the wagons, and they will come to the steel plants or the power plants. Okay. And in such a scenario, we had serious failures of the conveyor systems, because it was a new plant, new conveyors, new bearings, new motors, new gearboxes, but they did a lousy job in installation. Misalignment was there, and then this gave rise to a lot of high forces, unbalanced forces, and the whole thing, some of the components did break. Okay. So, we need to ensure that through vibration monitoring this can be avoided, okay, and this can be done. Another case of vibration monitoring which is done, this is the case of a permanently installed vibration monitoring of bearings. Okay. Particularly, this is the case of a paper mill. Okay. In paper mill, I don't know if you know how papers are manufactured. Basically, there are a lot of rolls. Okay. Lot of rolls rotating at different RPMs, could be at 1200 RPMs, and this paper actually, if I was to briefly tell you, this is a pulp of waste paper plus maybe some fresh wood pulp, which is made to a pulp after a chemical treatment. This is like a slurry of very almost full of water, okay, watery slurry. Okay. And this is fed onto a roll, okay, and which is spinning at high speed, these rolls. Okay. And because there is a lot of water, this has to be again pressed by heavy rolls, okay, and then there has to be a guide wire. Okay, and this rolls have to press against it as if you are squeezing the water out of it, and there will be a lot of water getting collected. Okay. And then there will be another series of rolls, okay, wherein some will be like this. Okay. And there is a series of rolls, etc. They are all rotating at very high speeds. Okay. And this rolls eventually they will be taking off, and then finally, and these are actually known as the dryer rolls. Okay. So, basically they are steam dried. So, this pulp is getting red, and this rolls could be as wide as about 4 meters. Heavy rolls rotating at about 1200 RPM. Series of such rolls, and these are another dryer rolls. So, basically we are drying the pulp, where the water has been squeezed off. Okay, then we are drying it, and then we have to calendar it. What is known as the calendering is kind of ironing it. Okay, and towards the end there will be a pickup roll. So, if you go to any paper mill, there are about maybe close to about 200 high speed rolls, okay, about each about 1 meter, 2 meter in diameter. 1 meter the initially one, and then they will later on thin down, and rotating about 200 rolls, maybe 100 rolls of the size of 1 meter in diameter, and then 4 meter in length, rotating at high speeds, and then finally eventually the paper comes out. And this is a view of the dryer rolls. If you can see the rolls here, and of course, all these rolls have to be supported on bearings. And imagine if one roll breaks or fails, your paper is going to get jammed and there will be no production. This is a continuous process. About 80 tons of paper comes out per day. Okay, this is continuously running. You feed in pulp, all you have to do is a series of rolls, pressing it, drying it, ironing it, or calendaring it, and then you have a pickup roll. And in such a rolling mill, because of the high temperatures, first of all, they have to run continuously, and because of this high temperature, there is extreme heat on the bearings of the rolls. Okay, the roll bearings have to be monitored, and they have to be lubricated, they have to be greased. Okay, and in such a plant, the bearings have to be monitored continuously, and to do that, at every bearing location, if you see the steel cables, steel rope kind of things here, these are actually the cables which are coming out from the permanently installed vibration sensors at each bearing location. So, if there is a roll number, they know the bearing number. Okay. And in such a plant, and this is in a paper mill, continuously the data is being recorded. Okay. There is another view of the on the other side. You will see this is again a transducer which is used to measure. This is one of the rolls of the paper mill, and you can see a lot of steam. These are all steam jackets, steam pipes are there to heat the dryer rolls. These are all steam pipes, and very high temperatures, rotating at high speeds. Every bearing has to be monitored continuously. Okay. And then all this signal comes to a monitoring station, wherein a person, the analysis person could be recording it and could be analyzing it, and there are automated alarm levels according to that standard. Whether the levels are high or low, they will let you know that we need to take precautions to reduce the levels of the signal and so on. Okay. And that is what is done in the monitoring of the bearings from the paper mills. Okay. Continuously we have to do that. Okay. Another case is the case of gas turbine. If you close look here, this is actually a gas turbine which is driving a generator. Many places they have gas turbines used to drive electric generators. Okay. Maybe in your naval frigates, etc., which are driven by gas turbines. Gas turbines drive generators. Generators are used to drive motors, which are used to drive propellers. Okay. Not directly coupled to the gas turbines. These generators are the power source of the plant, and of course, in the northeast of our country, we have a lot of gas turbine power plants, 20 megawatt, 150 megawatt power plants driven by gas turbines. All you do is a gas turbine fuel, put it in a gas turbine and then use it. So, here we are monitoring the gas turbine vibration levels by putting in an accelerometer. If you can see here, this is an ICP type of accelerometer, wherein this gives the power supply, and obviously the gas turbines are very noisy. So, you have to put a ear muff here, because it is a very noisy environment. This was in a test bed. We are monitoring the health of the gas turbine to do the health monitoring. So, in summary, we have to, while we are doing vibration monitoring, couple of things we have to keep in mind. One is the location. Okay. Locations always may not be accessible. Locations, so in that case, we have to use what is known as non-contacting type. Transducer like lasers, but for permanent mount we can put industrial accelerometer. By industrial, I mean industrial accelerometer is the same accelerometer, but very robust, which can be subjected to high levels of acceleration, which can be subjected to high temperatures, and they can be permanently mounted. But for vibration diagnosis, and for vibration monitoring, as long as I follow the ISO standards, I am doing good. But for vibration diagnosis, I need to record the time history either through a tape recorder or through a digital data recorder. I have to record simultaneously. Why do I record simultaneously? To retain the phase relationship. This is very important when we are doing the diagnosis. So, as a condition machinery fault diagnostics engineer, we would be more interested in recording the time history simultaneously, and then so that we retain the phase relationship, so that we can know the cause of vibration is important. Okay. Machines are going to give out vibration levels A, B, C, machine components at their characteristic frequencies. So, this information is not available if I just look at an RMS level of the vibration level from a permanently installed transducer. I will get a certain value. This only tells me whether the value is more or less than the acceptable level. But if I do a recording in the time domain, do an FFT analysis, see the individual components which have come up in the spectrum, and then relate these parameters F A, F B, F C to physical condition, only then can I say whether for the high levels of vibration, whether the component B is responsible or A is responsible or C responsible. I can do that. For example, if I was doing vibration monitoring in this way, I will be suddenly alarmed if this B was increasing. I will know, well, at all recordings my B levels are increasing. So, something is wrong with B. This would not be possible if I had just seen the overall level, overall RMS level from 10 to 1000 hertz. If I had seen the overall vibration level, I would not know whether it was A which is responsible for such a high level, or B whether it is responsible for a high level, or C which is responsible for such a high level. Okay. And so, what should be there in your vibration monitoring kit? Okay. In your vibration monitoring kit, we must have the transducer with its mounting accessories like magnets, studs, taps, etc., the cables, the power supplies, portable power supplies, the readout units either analog or digital. Transducer to measure rotation. Sometimes a data recorder, and of course, another very important thing is the handheld calibrator, typically which gives 10 meters per second square at 1000 radians per second. Okay. And of course, we have to have a writing pad to make a sketch of the measurement. Configuration. As to axial, vertical, horizontal, because we have to measure in axial, vertical, horizontal, and this is what has to be there in any vibration monitoring kit, which is used to, and you can have multiple number of transducers, okay, as the case may be. Okay. If you have, if you are carrying this equipment with you, and if you understand how to do that, and sometimes another question on this calibrator is usually this at 1000 radians per second, this means 159.2 hertz. So, if you look at the spectrum coming out of the calibrator, you will see a peak of 10 meters per second square at 159.2 hertz. Sometimes it is good to have this field calibrator just to check the sensitivity level, because you can be having power supplies and maybe a conditioner or a signal conditioner, like the charge to voltage amplifier. And another thing which we have to do in the accelerometer calibration calibrator in the lab before you go to the field to do the vibration monitoring is do an overall calibration, and this is done by this method. We have to in the lab, you can put an power amplifier, a random noise signal generator. This is an exciter, and onto this you attach an accelerometer. Which is a reference accelerometer, onto which we measure the test accelerometer. So, if you measure the transfer function between the test accelerometer and the reference accelerometer, if I know the reference accelerometer is good from a certain bandwidth, you should see a plot like this, whatever. So, this means the test accelerometer is behaving the same as the reference accelerometer for the all frequencies of excitation. So, this kind of calibration we cannot do in the field. Of course, these two signals have to be fed to an FFT analyzer, of course, important. Okay, and you just see the transfer function between this accelerometer and this reference accelerometer, divide one by the other, they should be the same, and that is why you will get this one value of 1. Once you are done that, you can be sure that this accelerometer, test accelerometer which you are going to take into the field, is calibrated for all frequencies. And at the field, you just give a known value of 10 meters per second square at 159.2 hertz and see whether they corresponds, you are getting the same value. Or if I get some x voltage in the system, I know this corresponds to 10 meters per second square. Okay. This can be done. Okay. So, this is very, very important, and as you know, there is a relationship between this 10 meters per second square at 1000 radians per second. Now, omega square a is the acceleration. So, this will boil down to 10 millimeters per second at 1000 radians per second, or 10 micron of displacement, because of the relationship omega a, omega square a and omega. So, this is a handy rule, and it is very easy to remember 1000. Actually, 1000 corresponds to 159.2 hertz, and that you can see in any FFT analyzer. Okay. So, in summary, to do vibration monitoring, you have to be careful about the equipment which you take, how you mount the accelerometers, and what kind of precautions you have taken to ensure that the accelerometers are properly calibrated, and what you get is what you should get. Okay, not that garbage in is garbage out. Okay, you have to ensure that you have measured correctly. Nothing like doing a correct measurement, because all your diagnosis depends on how you measure the vibration levels. Okay. Okay, thank you.